You know, back when I was just a kid working as a plumber in the Bronx, long before I ever dreamed of becoming a physicist, I used to think that space and time were simply there. They were like the iron pipes I spent my days fixing, solid, real, and about as fundamental as anything could get. But after decades spent wrestling with the strange rules of quantum mechanics, peering into the abyss of black holes and climbing the theoretical mountains of string theory, my mind has been completely turned inside out. I've come to believe that space and time are not the foundational bedrock of reality. They are what we call emergent. They arise from something deeper, something far more fundamental, and I genuinely believe this is the most radical, mind-bending idea in all of modern physics. Let me walk you through why I've come to this conclusion, and more importantly, why it should matter to every single one of us. For the vast majority of human history, we operated under a very simple assumption. We thought of space as a kind of empty container, a vast, silent void where things just happened. Isaac Newton, the father of classical physics, believed this deeply. For him, space was absolute, an unchanging stage upon which the grand drama of the universe played out. And time? Time was a separate, steady metronome, ticking away independently and identically for every person, everywhere in the cosmos. That was the picture, a fixed arena and a universal clock. Then, along came Albert Einstein, and he shattered that entire worldview with his theory of relativity. Einstein showed us that space and time aren't separate entities at all. They are woven together into a single, four-dimensional fabric called space-time. This fabric isn't static or rigid, it's flexible, dynamic, and alive. It bends, warps, and curves in the presence of matter and energy. It was a revolution that forever changed how we see the cosmos. But, and this is a critical point, even in Einstein's beautiful and elegant model, space-time itself is still treated as fundamental. It's the background, the canvas upon which everything else, all the particles and forces, paints the picture of reality. I am convinced this is not the end of the story. It's just a profound chapter. The cracks in this idea start to appear when you try to do something that should, in theory, be possible. Combine Einstein's general relativity with quantum mechanics. These two theories are the twin pillars of modern physics, our most successful descriptions of how the universe works. But the problem is, they absolutely refuse to play nicely together. On one side, you have quantum mechanics, a world of probabilities, uncertainties, and wild fluctuations where nothing is ever perfectly still. On the other side, you have general relativity, which describes spacetime as smooth, continuous, and predictable. When you attempt to apply the rules of quantum mechanics to gravity itself, to the very fabric of spacetime, the equations go haywire, you get infinities, you get predictions that are complete nonsense. This isn't just a technical glitch, it's a profound message from the universe. It's telling us that our current description of spacetime is breaking down. It's an approximation. It works beautifully at the scales of planets, stars, and galaxies, but it's not the ultimate truth. At the smallest possible scale, the Planck scale, something entirely different must be happening. Something far more fundamental than our familiar notions of space and time. My own personal obsession with black holes began decades ago, and it's these cosmic enigmas that truly convinced me that space and time cannot be fundamental. Let's think about what happens at the edge of a black hole, the event horizon. Imagine you're watching a friend fall into one from a safe distance. From your outside perspective, something incredible happens. You see your friend slow down, their movements becoming sluggish as they approach the horizon. They appear to freeze in place, and it looks like their information is smeared across the horizon itself. Now imagine being your friend. From their perspective, they feel nothing special at the horizon. They just keep falling right through it, as if it's not even there. Here's the crucial point. Both of these perspectives are completely valid. They are both correct descriptions of reality, yet they describe wildly different geometries, different arrangements of space and time. How can that be possible if space and time are truly fundamental, objective things? The answer, I am now convinced, is that they aren't. They are descriptions. They are ways of organizing and making sense of something far more fundamental, something that exists beneath the surface of reality. This line of thinking brings me to one of my favorite and most powerful ideas in theoretical physics, the holographic principle. This is a concept that my brilliant colleagues Juan Maldacena, Gerard 't Hooft, and I explored from different angles, and it has become absolutely central to our modern understanding. In simple terms, the holographic principle proposes that everything happening inside a volume of space can be completely described by information encoded on the boundary of that space. Think of a hologram on a credit card. That's a two-dimensional surface that encodes all the information needed to create a full three-dimensional image. The principle suggests the universe might work in a similar way. For a black hole, this means that all the information about everything that has ever fallen into it is encoded on its two-dimensional event horizon. In a very real sense, the interior, the three-dimensional volume, is redundant. It's not fundamental. It emerges from the information on that boundary. This is wild stuff. It suggests that one of our fundamental dimensions of space, the radial dimension pointing into the black hole, is not fundamental at all. It emerges from the physics on the boundary. And if this is true for the most extreme objects in the universe, it might be true for everything. This idea was made mathematically concrete by Juan Maldacena in 1997 with his discovery of the AD-CFT correspondence. This is, without a doubt, one of the most important breakthroughs in theoretical physics in my entire lifetime. Here's the core of it. You can have a quantum field theory, a description of particles and forces that lives on the boundary of a space, and this theory contains no gravity. It's just quantum fields interacting according to their own rules. But this theory is exactly equivalent in every possible way to another theory, a theory of gravity that includes the existence of a full dynamic space-time in the interior bulk of that space. The boundary theory has one fewer dimension and has no concept of gravity, and yet, from that boundary theory, you can derive the existence of the bulk space-time. Space, time, and gravity, everything, emerges from the quantum interactions and entanglement happening on that lower dimensional boundary. This isn't just a vague philosophical speculation, it's a precise mathematical correspondence. You can perform calculations on one side and the other and get the exact same answers. To me, this is the ultimate proof of concept. It shows us, with mathematical rigor, that space-time can be emergent. So, if space isn't fundamental, then what is? What is the true bedrock of reality? I believe the answer is quantum entanglement. Entanglement is that famously spooky connection between particles that so troubled Einstein. When two particles become entangled, they lose their individual identities. Measuring a property of one instantly influences the other, no matter how far apart they are, across a room or across the universe. Einstein called it spooky action at a distance. But it's a real verified phenomenon. We've proven it in experiments countless times. Now here's the key insight. Entanglement creates a relationship, a fundamental connection between quantum bits of information. And I believe this intricate web of entanglement, this network of relationships, is what gives rise to the very fabric of space itself. Imagine space emerging from the patterns of entanglement between countless quantum degrees of freedom. Points in space that are near each other correspond to quantum systems that are strongly entangled. Points that are far apart correspond to systems that are only weakly entangled. In this revolutionary picture, geometry, distance, and space itself are all derived from the underlying structure of quantum entanglement. A few years ago, Juan Maldacena and I proposed an idea that takes this connection even further into territory that seems almost too crazy to be true. We called it ER Gyakurs EPR. On one side, ER stands for Einstein-Rosen bridges, what we commonly call wormholes. These are theoretical shortcuts through space-time, tunnels connecting distant regions of the universe. On the other side, EPR stands for the Einstein-Podolsky-Rosen paradox, the famous thought experiment that first described quantum entanglement. Our proposal is stunningly simple. They are the same thing. An Einstein-Rosen bridge is an EPR pair. A wormhole and a pair of entangled particles are two different descriptions of the exact same underlying phenomenon. When two black holes are deeply entangled, there is a wormhole, a geometric connection, linking them. The wormhole is the physical, geometric manifestation of their quantum entanglement. This idea directly and powerfully connects the geometry of space-time to the language of quantum information. It's yet another piece of overwhelming evidence that space-time emerges from the strange rules of quantum mechanics, not the other way around. If space is emergent, then what about time? This is an even more profound and mysterious question. In standard quantum mechanics, time is treated differently than space. It's a parameter, a background variable against which change is measured. You can't measure it with an operator the way you measure position or momentum. In general relativity, time is woven into the fabric of space-time, interchangeable with space depending on your motion. But in the search for a theory of quantum gravity, time seems to be an emergent property, just like space. At the most fundamental level of reality, there may be no time at all. There may be only timeless quantum information. Time, with its direction and its flow, may only emerge when you coarse-grain, when you zoom out and look at the universe on larger, less fundamental scales. This idea is deeply unsettling. Our entire existence, our every thought and experience, is structured by time. Cause and effect, memory, aging, hope, everything depends on the arrow of time pointing from the past to the future. But that arrow, that flow, might be a beautiful illusion, an emergent property of our own macroscopic perspective. The Wheeler-DeWitt equation, a key equation in quantum cosmology, famously has no time variable in it at all. It describes a timeless universe. Time only appears in the equation when you begin to ask questions about the correlations between different parts of the universe. This strongly suggests that time, like space, is not woven into the deepest fabric of reality. Let me give you a simple analogy to make this more intuitive. Think about temperature. Temperature feels incredibly real and fundamental to us. You can measure it with a thermometer, you can feel it on your skin. But we know from physics that temperature is not a fundamental property of the universe. It's an emergent phenomenon, a statistical average of the kinetic energy of countless molecules in motion. At the level of a single molecule, the concept of temperature has no meaning. It only makes sense when you have a huge collection of molecules and you zoom out to look at the big picture. I believe space and time are just like temperature. They are incredibly useful, indeed essential, descriptions of reality at our scale. But they break down completely at the fundamental quantum level. At the Planck scale, there are no smooth coordinates, no continuous flow of time. There is only quantum information, qubits of data entangled in intricate and complex patterns. When you have enough of these qubits entangled in the right ways, space emerges, time emerges, geometry emerges, and gravity emerges. Everything we perceive as the solid, concrete fabric of reality is actually an emergent phenomenon, as emergent as temperature is from the motion of molecules. This idea carries profound implications. It means that asking what happened before the Big Bang might be a question that doesn't even make sense. If time itself emerged at the moment of the Big Bang, then there was no before. It's like asking what is north of the North Pole. The question itself assumes a framework, a direction called north, that simply doesn't exist at that point. It also fundamentally changes our goal in the search for a theory of everything. We are no longer looking for a set of fundamental equations written on a fixed background of space and time. Instead, we are searching for the fundamental rules that govern quantum information, the rules from which space-time itself emerges as a secondary property. String theory is one powerful approach to this. In string theory, the fundamental objects are tiny, vibrating strings in higher dimensional spaces. The way these strings vibrate determines the properties of particles, forces, and even the geometry of space-time itself. The geometry isn't fixed. It's determined by the quantum state of the strings. Loop quantum gravity is another major approach. It proposes that space itself is quantized, made of discrete, indivisible chunks at the Planck scale. Space becomes a network of quantum connections, and the smooth, continuous geometry we experience emerges only when you look at this network from a distance. Both of these approaches, in their own ways, point to the same conclusion. Space-time is not the foundation. it's the building. One of the most thrilling developments in recent years has been the deepening connection between quantum information theory and gravity. We've come to realize that concepts from computer science and information theory, things like quantum error correction and computational complexity, are intimately and deeply connected to the geometry of space-time. For instance, the amount of entanglement between two regions of space is directly related to the area of the minimal surface that separates them. This is the famous Ryu-Takayanagi formula, and it's a breathtakingly beautiful link between the abstract world of quantum information and the geometric world of space. The geometry of space literally encodes how much quantum information is shared between its different parts. There's also a developing idea that the computational complexity of a quantum state, how difficult it is to compute its evolution, is related to the volume of space-time in certain geometries. The more complex the quantum state becomes, the larger the corresponding space-time volume grows. This hints that the passage of time might be related to the growing complexity of the quantum state of the universe. Think about it. As time marches on, the universe becomes more complex. Entropy increases. Quantum states evolve and become more entangled and more difficult to describe. Maybe that's what time really is, the direction of increasing complexity. This could finally explain the arrow of time, why it flows in only one direction. It's not a fundamental law of physics. It's a consequence of the universe starting in a very special, low entropy, low complexity state, and naturally evolving towards states of higher entropy and higher complexity. Now, you might be wondering, if all of this is true, why does space seem so incredibly real to us? Why does it feel like the most fundamental thing there is? The answer is emergence. At our scale, with our human senses and our everyday instruments, the emergent description of reality is perfectly valid and accurate. Space and time work beautifully for describing the physics of baseballs and cars, of planets and stars. Even Einstein's relativistic space-time is a magnificent and accurate description for almost everything we observe in the cosmos. It's only when you push reality to its extremes, inside black holes, at the moment of the Big Bang, at the quantum gravity scale, that the emergent description breaks down and you are forced to use the more fundamental information-based description. It's exactly like Newtonian mechanics. It works perfectly for launching a rocket to the moon, even though we know it's not the most fundamental description of reality. Einstein's relativity is more fundamental, but for most everyday purposes, Newton is more than good enough. In the same way, Einstein's space-time is an excellent, accurate description for almost all purposes, but at the deepest level, it is emergent from a substrate of quantum information. We are peeling back the layers of reality, and each layer we uncover is more fundamental than the last. This incredible journey from space and time as absolute and fundamental, to relative in Einstein's theory, to emergent from quantum entanglement, has taken over a century of the most brilliant thinking humanity has to offer, and we are not done yet. We still don't have a complete testable theory of quantum gravity. We don't fully understand the precise mechanism by which space-time emerges from quantum information, but the pieces of the puzzle are falling into place. The holographic principle, ADS, CFT, ER, or EPR, the connections to quantum information theory, all of these powerful ideas are telling us the same compelling story. Space-time is not the fundamental stage on which the drama of the universe is performed. It is part of the drama itself. I find this realization incredibly exciting. It means that reality is far stranger, far richer, and far more interesting than we ever imagined. The universe isn't a stage where things happen. The universe is information. It's quantum information, organized and entangled in exquisitely complex patterns. And from that fundamental information, everything we know and experience, space, time, matter, energy, gravity, everything emerges. This fundamentally changes how we should think about the universe at its most basic level. Instead of asking, what is the geometry of space-time? We should be asking, what is the pattern of quantum entanglement? Instead of thinking about particles moving through space, we should think about quantum information being processed and transformed. The universe, in a very real and profound sense, is a kind of quantum computer. not a computer sitting in space, but a computer whose very computations generate space. Every single interaction, every quantum measurement, every bit of entanglement is part of a vast cosmic computation that creates the reality we perceive. Now, I want to be perfectly clear. This is still an incredibly active area of research. We are far from having all the answers. We are still working out the details, still wrestling with the deepest puzzles. But the overall picture, that space-time is an emergent phenomenon from a deeper layer of quantum information, is becoming more compelling, more mathematically rigorous, and more widely accepted with each passing year. One of the biggest open questions is, what are the fundamental degrees of freedom? What are the actual qubits from which everything emerges? In string theory, it might be strings and brains. In loop quantum gravity, it's spin networks. In other approaches, it might be something entirely different that we haven't even conceived of yet. We simply don't know for sure. Another huge question is the exact mechanism of emergence. How does the smooth, classical space-time we experience arise from the quantum foam of information? We understand this process in certain special cases, like in the ADS-CFT correspondence, but we are still far from having a general comprehensive theory. We need to understand the mechanism of emergence far better. And then there's the deepest question of all, time. If time is truly emergent, how do we describe dynamics? How can anything change if there is no fundamental time parameter for it to change in? This is a profound conceptual puzzle that continues to challenge the greatest minds in physics. But despite all these open questions, the evidence continues to mount. Every time we dig deeper into quantum gravity, every time we study black holes with more sophisticated tools, every time we explore the connections between quantum information and geometry, we find more and more support for this radical idea. This is why I am so deeply passionate about this topic. It's not just an abstract, esoteric, theoretical idea for physicists to debate in ivory towers. It is a fundamental shift in our understanding of reality itself. It is as radical, as world-altering, as the shift from a geocentric to a heliocentric model of the solar system, or from classical mechanics to the weirdness of quantum mechanics. We are living through a revolution in physics right now, and most people have no idea it's happening. The very fabric of reality, the stage upon which we believe everything happens, is not what we thought it was. It's an emergent phenomenon arising from something deeper and stranger. And here's the truly beautiful thing. This idea makes the universe more unified and more elegant. Instead of having matter, energy, forces, and space-time as separate fundamental entities, we have just one thing: quantum information. Everything else, the entire richness and complexity of the cosmos, emerges from it. This is the dream of physicists from time immemorial, a simple, unified description of reality. Not simple in the sense of being easy to understand, but simple in the sense of having very few fundamental ingredients. One fundamental thing, quantum information, from which all of physics emerges. Einstein spent the last 3 decades of his life searching for a unified field theory, a single framework that would unite all the forces of nature. He never found it, but I believe we are getting close. The unification, when it comes, will not be what Einstein expected. It won't be a geometric unification of forces. It will be an informational unification. Everything emerging from the patterns and flow of quantum information. And the potential implications of this go far beyond just understanding the universe. If we ever truly understand how space-time emerges, we might, in some far-off future, be able to engineer it. We might be able to create artificial space-times, manipulate geometry in ways we can't even begin to imagine today. This is, of course, far future science fiction, but the sheer possibilities are mind-boggling. More immediately, a deeper understanding of emergent space-time could help us solve the biggest puzzles in cosmology. What really happened at the Big Bang? What lies at the heart of a black hole? What is the true nature of dark energy? These questions all involve the intersection of quantum mechanics and gravity, and they may all find their answers once we fully understand how space-time emerges. The Big Bang might not be a true singularity at all. It might simply be a point where our emergent classical description of space-time breaks down, while something perfectly regular and comprehensible was happening at the fundamental quantum information level. The interior of a black hole might be completely encoded on its event horizon, resolving all paradoxes about information loss. Dark energy, the mysterious force accelerating the expansion of the universe, might be related to the large-scale structure of quantum entanglement in the vacuum of space-time. We don't know yet. But these are the kinds of profound questions we can finally begin to address with this new emergent space-time framework. Let me share something personal with you. When I first began to seriously consider these ideas, decades ago, they seemed crazy even to me. The notion that space and time might not be fundamental sounded like the stuff of philosophy or mysticism, not hard-nosed theoretical physics. But the more I worked, the more I wrestled with the mathematics of black holes, the more I explored the landscape of string theory and holography, the more I was forced to this conclusion. It wasn't that I wanted space and time to be emergent. It was that the physics itself demanded it. The math, the need for internal consistency, the strange and beautiful behavior of black holes, everything pointed in the same direction. The universe was telling us something profound, and as scientists, it was our job to listen. This is how science works at its absolute best. You follow the evidence, even when it leads you to the strangest, most counterintuitive places. You let nature surprise you. And time again, nature has surprised us with just how strange and beautiful it truly is. The idea that space and time are emergent is just the latest in a long and glorious line of surprises, but it fits perfectly into a long and noble tradition. We once thought the Earth was flat. It's round. We thought the Earth was the center of the universe. It's not. We thought time was absolute. It's relative. We thought the universe was eternal. It had a beginning. Each and every one of these discoveries shattered our previous worldview and expanded our understanding, revealing a universe far stranger and more wonderful than we had ever imagined. And now we are learning that space and time themselves, the very arena of existence, are not the final reality. They are emergent patterns woven from the thread of quantum information, and I think that is absolutely beautiful. It's a deep, profound insight into the ultimate nature of reality. So, where does this leave us? What are the key takeaways from all of this? First, be deeply skeptical of anything that seems obviously fundamental. Nature has a long and persistent habit of surprising us when we look closer. Second, pay attention to information. Information is more fundamental than matter, more fundamental than energy, and even more fundamental than space-time. The universe, at its core, is information. Third, embrace the weirdness. Quantum mechanics is weird. Relativity is weird. The idea of emergent space-time is weird. But weird does not mean wrong. In fact, the history of physics teaches us that the truth is often far weirder than we could have ever imagined. And fourth, and most importantly, stay curious. We do not have all the answers yet, not even close. The story of emergent space-time is still being written, and we are all living through its most exciting chapters. I have spent my entire career working on these ideas, wrestling with these puzzles, and I can honestly say that I am more excited now than I have ever been. We are standing on the verge of understanding something truly profound about reality. The next few decades are going to be absolutely crucial. New experiments, new observations from powerful telescopes, new theoretical breakthroughs, they are all on the horizon. And when we finally crack the code of quantum gravity, when we finally and fully understand how space-time emerges from the ethereal dance of quantum information, it will stand as one of humanity's greatest intellectual achievements. It will rightfully take its place alongside Newton's laws of motion, Maxwell's equations of electromagnetism, Einstein's theories of relativity, and the quantum revolution of the 20th century. I am deeply honored to be a small part of this incredible journey, and I truly hope that I have managed to convince you that space and time are not the final, fundamental layer of reality. They are emergent, and that changes everything.